Bismillahirrahmanirrahim. In this lecture, we study more about mediators. As discussed in the previous lecture, a mediator is in the middle of a pathway. Lemons prevent scurvy, but they act through vitamin C. So vitamin C is the mediator in this causal pathway. We start with a discussion of an interesting version of Simpson's paradox. Apparently, average wages have been growing according to some statistics, but falling according to others. A detailed examination shows that the median US wage has risen about 1%, but in every educational group, the median wage has gone down. So how can it be that every group wage is going down, but the overall wage is rising? That's an example of the Simpson's paradox. This is an illustration of the main phenomena we are studying in this lecture, which is called partial mediation. As time proceeds, this is an exogenous unknown factor, which is basically the dynamics of the economic process. It affects the wages in both in all educational sectors, which we will take for simplicity to be white and blue. The wages, in fact, might be declining in each sector. But also the composition of the groups is changing. So if we look at only one channel, if we look at the wages and they have been declining, then we say, oh, total wages must be going down. But there is another channel through which the dynamics of the economic process acts. And this other channel is the proportion of white and blue collar workers. And if the proportion of the population in white collar jobs which have higher wages increases, that can offset the decline in wages in the sectors. We will show this in numerical detail in the next slide. These are hypothetical figures. Suppose that the labor force is divided into half and half, blue and white collar. The blue collar workers earn 100 and the white collar workers earn 1,000. Then the total wages come out to be 50 times 100 plus 50 times 1,000, which is 55,000. Now suppose as time changes, more people decide to get educated. So we have now 60% white collar and 40% blue collar. And suppose that wages in each sector have been declining by 10%. So instead of 100, blue collar workers are earning only 90, and white collar workers are only earning 900. Then the total wages come out to be 73,360, which is much larger than 55,000. So even though the wages declined in each sector, the proportion of laborers deciding to get educated increased, and so the overall wage increased. And so basically, if you look at the two different channels through which time acts, one channel is showing a decrease, the other channel is increase, and the combined effect will determine the outcome. We can revisit the Berkeley admissions paradox and see that it is a case of the same phenomena. There are two mediating factors which determine the average admission rate for any group of applicants. One is the admission rates in the two departments, and the other is the proportion applying to the two departments. So suppose that for one group, like females, the admission rates are higher in both literature and engineering. This will have a positive effect on the average admit rate. But there is another mediator, and that is the proportion which applies to literature versus English. If literature has a tough admissions policy and engineering has an easy admissions policy, and the females apply in huge numbers to literature and not to engineering, then this negative factor will overwhelm the positive bias in admissions. So basically, if two channels work in opposite directions, then either one can overwhelm the other. The article by Bickle, which first investigated this admissions paradox at Berkeley, differentiates between bias and discrimination. Bias he calls the statistical outcome that maybe there are more males than females in Berkeley. And discrimination is an effort by the university to prefer one or the other gender. So if you look at the departmental admissions processes and you discover that all of them are trying to favor females, then you know that there is no discrimination. If you see that the result nonetheless is overall bias against females, this is not the result of discrimination, but it is a result of some other factor. In particular, the factor that Bickle identified was that females choose the harder departments to get into. Next, we look at another case of partial mediation, and this is another type of Simpson's paradox. We have this drug which is seems to be good overall. We have a treatment group with 1,000 people who took the drug and a control group which did not take the drug. In the control group, only 440 people recover from the disease, and in the treatment group, 560 people. So 56% recovery rate with drug and 44% without means that the drug is good. But suppose that we subdivide the population into high blood pressure types and normal blood pressure types. We find that in both groups, the drug acts unfavorably. In the high blood pressure group, the recovery rate in the control group is higher, and in the treatment group is lower, and similarly in the normal blood pressure group. So the question is, why? How can the drug be bad for people with high blood pressure and bad for people with normal blood pressure, but good for people in general? This is another case of the Simpson paradox. Here are the specific numbers. Suppose that the control group has 900 people with normal blood pressure and 100 with high blood pressure, and the recovery rates in the control group are 80% and 40%. So you can calculate that 80% of the high blood pressure people will recover, and that will give us 80 recoveries, and 40% of the normal will recover, and that will give us 360 recoveries for a total of 440. But now in the treatment group, for some reason, and this is something that we need to learn more about, there are 900 people with high blood pressure and 100 with normal. Because the recovery rates are much better in high blood pressure, the bias in the treatment group that there are so many high blood pressure means that even though the treatment lowers the recovery rate is 80% in control group but only 60% in treatment group, the recovery still leads to 540 recoveries. And in the normal blood pressure group, again, instead of 40%, we have lower recovery at 20%. So overall, the effect is that there is more recoveries in the treatment group, even though the drug is bad in each of the two subgroups. So basically, there are two channels for the overall recovery rate. One is the action of the drug, and the other is the proportion of high blood pressure to non-blood pressure. So in the treatment group, the higher recoveries is due to the higher proportion of high blood pressure people who have better recovery rates in general, and not due to the action of the drug. So which figure should we trust? Should we say that, well, overall the drug is good and so we should administer it to everybody? Or should we look at the subgroup figures which show that the drug is actually bad for both normal blood pressure and for high blood pressure? There are two different factors which affect the mortality rate. One is whether the person is being treated or whether he is in the control group or not being treated. And the other is the proportion of the high blood pressure to no blood pressure. The paradox that we saw occurs because these two things act in different ways. The treatment actually worsens the recovery rate, but the high blood pressure improves the recovery rate. So if the treatment and control group differ in these two factors, then it is the combined effect of the two which can go in either direction. So now the question is, which of these two figures to trust? The answer to this depends on the causality, the path diagram between HBP and treatment and control. Why are there so many high blood pressure people in the treatment group? Is it that because the experimenter chose groups in this way, or is it because it's an effect of the drug? This is crucial to answer, but the answer is not in the data. This is very important. So there are two possible cases. One case is then the high blood pressure and normal blood pressure is an exogenous variable. For example, suppose that the drug trials are given in a hospital where they are treating high blood pressure people and they have access to these, so they gave them all the drug, and they took people off the street for the control group, and there was normal blood pressure. So in this case, HBP or high blood pressure is what is called a confounder. High blood pressure was given in advance, that was the population in the hospital, and then we chose to put them into the treatment group. So the causal arrow runs from the proportion to treatment and control, and it also affects the mortality rate. So this is the first picture, the first diagram, in which the causal arrow runs in this way. The treatment does not cause high blood pressure or normal blood pressure. It is the other way around. In this case, this acts like a confounder, which we have studied earlier and we'll study some more later. In the other case, it's possible that the drug creates high blood pressure. So the drug actually has a damaging effect on recovery, but it has a side effect of increasing blood pressure, and this side effect is actually beneficial for the disease. So the drug acts through two channels. One channel is direct, and that effect is bad, but the other channel is indirect. It raises blood pressure, and that is helpful in overcoming the disease. So if in this case high blood pressure is a mediator, then the overall mortality rate is what we should look at. And so then we should administer this drug, and the subgroup rates are not relevant. So because when you want to calculate the effect of the drug, you want to calculate both channels, the direct and the indirect. So the answer to the question of whether we should look at the subgroup rates and conclude that the drug is bad, or whether we should look at the overall rates and conclude that the drug is good, depends on the causal relationship between high blood pressure and treatment and control. In one direction, the overall result becomes better, and in the other, the subgroup result becomes the correct and reliable result. We've already discussed confounding earlier, and we will discuss it again in next lecture, where we will consider a different solution called randomization. But here we say that the idea that there is a causal path from high blood pressure to treatment is not very plausible in this diagram. What the causal path arrow suggests is that the patients self-select. The high blood pressure patients select to be treated, and the normal blood pressures prefer to be controls. This can happen in certain examples, and there are examples of this happening. But a more plausible thing is that the patients are assigned to one group, the treatment and control group, by the experimenter, and for some reason the experimenter doesn't match the two groups and chooses a lot of patients from the HBP in treatment. For example, the experimenter might be working at a hospital and chooses all patients coming in who are then likely to have high blood pressure, and the controls are chosen from the normal population. In this case, the HBP and treatment will be correlated because of a common cause, and this is sufficient to create confounding. So how can we tell if high blood pressure is a mediator or a confounder? The answer to this determines whether we should administer the drug or not. Well, the answer is not going to be in the data. You have to look at the real world mechanism, you have to look at how the drug operates, you have to look at how the patients were chosen, and these things are not part of the data. Basically, as we have been discussing throughout the course, data by itself is not enough to tell us the answers to the questions that we want to know. In particular, causal relationships are not on the surface at the level of the data, they are in the underlying structures of the real world, which must be explored. So basically, we can summarize this lesson by saying that the partial mediation occurs when X acts on Y through two channels. One is the direct channel, X directly affects Y, and the other is mediated through this mediator M. So X acts on Y and also X causes M, which causes Y. The total effects on Y is the combined effect through both channels. Simpson's paradoxes arise when one channel acts in one direction and the other channel has the other direction effect. So sometimes the direct effect is overwhelmed by the indirect effect, and that leads to the Simpson's paradox. Just one more example from literature is that people come into playing games. People are used as experimental subjects in the prisoner's dilemma game, and people come in with either a cooperative attitude or a competitive attitude. The competitive attitude people like to take advantage of others and are greedy and selfish. The cooperative attitude people like to play along with others and cooperate, especially if they expect the others to cooperate. So there have been experiments conducted in which after the subjects come in, they are primed, they are given some information or some reading or some motivational pep talk to induce them to cooperate or to compete. So priming is a method of putting the subject experimenter in a certain frame of mind. So it turns out that people with competitive attitude always are not much affected by priming, and they act in the same way as they would otherwise in the prisoner's dilemma. But the people with cooperative attitude are very much influenced by priming because they think about how the other party will behave, and they like to cooperate if the other party is cooperate, but they will also betray if the other party is not cooperative. So the priming sets their expectations about others and changes their behavior. So there are two channels by which the behavior in the prisoner's dilemma is affected. One is the direct effect of the basic personality type of the player, and the other is the priming factor. And you can separate out these two effects and do various types of calculations. Here's another case of a partial mediator. As we find that as age increases, the blood pressure also increases, but there is a mediator weight. As age increases, also people gain weight in general, and so there are two pathways by which age acts on blood pressure. One is the direct pathway and the other is through weight. So the overall effect can be decomposed into these two effects, and sometimes it's useful to learn of these two effects. For example, if the larger effect is coming through the weight, then diet and other measures for weight control would be effective in preventing blood pressure. But if the larger portion of the effect is coming through directly through age, then diet will not matter so much. So learning how to break down the overall effect into the direct effect and indirect effect is one of the major goals of mediation analysis. So to conclude, we recall that if X affects M and M affects Y, M is the mediator on the causal path between X and Y. If M is the full mediator, there is no other pathway, then M screens the effect of X on Y. Once we know M, we don't need to know X, and because the value of M is what will determine what will happen to Y. But if M is a partial mediator, then X acts on Y through other channels, and so knowing M will only give us one channel of the effect of X on Y, and there may exist other channels, so the total effect will be the effect through all the channels. And for some policy questions, it's useful to be able to separate the total effect into effects through M and the other effects, or direct effects and indirect effects.